demonstration is a simulation of a rubber molecule in motion. Rubber belongs to a class of materials called high polymers. Polymers make up the clothes I wear, the leather in my shoes, the plastic in my pen, even the protein in my body. Polymer means many parts and comes from the fact that a typical polymer molecule, here is a model of one, is composed of many parts, all hooked together in a long chain. In this film, you will see how the size and shape of such giant molecules, the way they pack together, and the strength of forces between them affect the physical properties of polymers. Let's turn our attention to size. The gas methane, the liquid octane, the soft wax paraffin, and the flexible plastic polyethylene are all composed of carbon and hydrogen atoms in about the same ratio. But their molecules differ in molecular weight or in the number of atoms per molecule. A methane molecule consists of a single carbon atom bonded to 4 hydrogen atoms. Removing one of the hydrogen atoms makes a chemically active molecular fragment which can grow by adding a succession of CH2 groups until growth is stopped by addition of a single hydrogen. This structure has 8 carbons and 18 hydrogens and represents an octane or gasoline molecule. Here is a model representing a paraffin wax molecule. The model has 32 carbon atoms and 66 hydrogen atoms. By adding more CH2 groups, molecules can grow until about 1,000 carbon atoms and twice as many hydrogen atoms are in one chain. Such a molecule is a hydrocarbon called polyethylene. A model of polyethylene on this scale would span hundreds of feet. However, actual polymer molecules are seldom longer than 1/10,000th of an inch. Sometimes a molecule grows branches along its backbone which contain additional carbon and hydrogen groups. Also, in some cases, carbons from one chain form strong bonds with carbons from other chains to make a single gigantic molecule. You have seen how we can build polyethylene molecules by linking together CH2 groups in a long chain. Not all giant molecules are as simple as this. Some polymers contain other atoms, such as chlorine, oxygen, and nitrogen. Here is a drawing of polyvinyl chloride. It is very similar to polyethylene. However, on every second carbon atom, a chlorine atom replaces a hydrogen. The nylon molecule is considerably more complicated. You can see from the drawing, though, that it contains both oxygen and nitrogen. The atoms in all of these molecules are held tightly together by a type of bond which we call covalent. However, even after an atom forms a covalent bond, it still has an electrostatic attraction for its neighbors. If the attraction or cohesive energy between molecules is larger than their energy of motion, the molecules will stick together and form a liquid or solid. In fact, one way we determine cohesive energies is by measuring boiling points. On this chart, you can see that boiling points rise as molecules increase in size, which tells us that cohesive energies go up as molecules get larger. Now, in addition to size, there are other factors that can raise cohesive energies. For example, this molecule, methyl chloride, is very similar to methane, but has a chlorine atom in place of one of the hydrogens in methane. The chlorine raises the cohesive energy significantly. The boiling point of methyl chloride is up around 0 degrees centigrade, 160 degrees centigrade above the boiling point of methane. Polymer molecules that contain chlorine, oxygen, or nitrogen are called polar molecules. They have higher cohesive energies than nonpolar molecules such as polyethylene. However, because they are so large, all polymer molecules, whether polar or not, have reasonably high cohesive energies. These energies have a very important effect on many polymer properties, among them the melting point. Melting points can be determined on a special hot plate whose temperature rises along its length. The samples to be melted are all hydrocarbons ranging in size from about 1,000 carbon atoms to 30. As they melt, they become clear. Wax melts at about 60 degrees centigrade. The cohesive forces between small wax molecules are relatively weak. This sample melts at about 80 degrees centigrade because the cohesive forces between these larger molecules are greater than those in wax. Here the melting point is above 130 degrees centigrade, somewhat higher than the previous sample. But this molecule is 10 times larger. Melting points do not increase in direct proportion with sizes. This curve for nonpolar molecules shows the relationship between the melting point and the average number of carbon atoms in the chain. Melting points rise quite rapidly up to about 80 carbon atoms, more slowly above 100 carbon atoms, and finally reach a limit when molecules contain several hundred carbon atoms. For nonpolar linear molecules, the limit is close to 140 degrees centigrade. For comparison, here are two samples containing polar molecules. Polyvinyl chloride, or PVC, simply becomes soft at about 150 degrees centigrade, and even at 200 degrees centigrade, nylon is hardly affected. The higher cohesive energies of these polar molecules are reflected in their greater resistance to melting. However, other factors, such as the structural regularity or crystalline content, also affect melting points. For example, this linear polyethylene has more structural regularity than this branch sample. This material melts at about 115 degrees centigrade, 20 degrees lower than the linear polymer, because the chain branches inhibit crystal growth and also introduce imperfections in crystal structure. The polymers we have talked about so far are called thermoplastics because they melt and can be molded or extruded into various shapes. Their applications depend mostly on the properties we have discussed. For example, if we want a hard, rigid plastic, we use a polar molecule such as nylon that will crystallize well. Polyvinyl chloride is ordinarily very stiff. If we want to make this material softer or more flexible, we add smaller molecules called plasticizers. Then we get a rubbery plastic like this. If we need an especially good electrical insulator, neither of these materials will do. But polyethylene, like wax, is an excellent dielectric. So we insulate telephone wires with polyethylene. As you might suspect, though, branch polyethylene is not very strong. I can stretch this sample easily. I cannot do this to this linear sample, no matter how hard I try. Its highly crystalline structure makes it stiff and strong. To study this material, we use a large tensile test machine. The sample at first resists stretching, then it suddenly necks down and elongates. During the test, the machine records the stress strain data. Finally, the sample ruptures. Here is a stress strain curve made from data taken by the machine. At first, the sample resists elongation. X-ray studies show that initially, the crystals do not face in any particular way. They are unoriented. Then, at a critical stress, the sample yields and flows. Molecules straighten out and are rearranged. X-ray study of elongated samples indicates that the crystals are now oriented into particular directions. When molecules are stretched to their limit, and orientation is complete, in this case after 600% elongation, flow ceases. Then the sample ruptures. Here it is. Compare it with this sample which has not been drawn. These black grid lines on the original sample become these smeared blobs on the stretched piece. During drying, the cross-section of this sample decreased by a factor of about 20, while its stress resistance just before fracture was over half what it was before flow started. Thus, the strength per unit cross-section, or tensile strength, increased enormously. However, this high tensile strength is not the same in all directions. Crosswise, the sample is weak. It tears rather easily, and I can see little fibrils sticking out. Under the microscope, its fibrous structure is clearly apparent. In fact, we have converted the polyethylene plastic into a fiber. It is seldom found in textiles, though, because polyethylene melts at 135 degrees centigrade, well below the temperature used in ironing clothes. This chart compares melting points for several materials. A textile fiber, such as nylon, contains polar molecules and has a melting point above the ironing temperature. The polar bonds in cotton are so strong that it won't melt at all. It decomposes at high temperatures. So far, we have discussed plastics and fibers. What about rubber? How does it differ from these materials? To begin, look at the melts of different sized molecules. Here is a melt of ordinary wax. It is quite liquid and runs freely. This melt is not nearly so mobile. It has a high viscosity. This material is a short chain linear polyethylene. Now look at this melt of a cross-linked polyethylene. It is rubbery. In fact, the polyethylene in this state is actually a rubber, not a very useful one, but nevertheless a rubber. Rubber molecules can be understood by watching what happens to these beads in this tank of water. They can be agitated somewhat randomly by the water jets at the corners of the tank. The rubber molecule is characterized by its giant length and freedom of movement. Thermal motion tends to cause the ends of the molecule to draw together, as you see here. Since this is so, stretch rubber contracts when it is heated, instead of expanding as most materials do. Here is a rubber band which is being stretched so that it balances a weight. When the rubber is immersed in hot water, it shrinks. And when it is put in cold water, it expands. This simulation of the rubber molecule provides a way to explain the behavior of rubber shown in the previous demonstration. The disorder caused by thermal agitation or heat makes the ends of the giant rubber molecule draw together. If order is imposed on such a chain by pulling its ends, it gives up energy or heat and raises the temperature of its surroundings. Then, when the ends are released, energy is absorbed and the temperature of the surroundings falls. Stretching releases heat. Contraction absorbs heat. This can be demonstrated. The glass bead contains a device to measure small changes in temperature. Heat makes the pointer swing to the right. Now, as the rubber is stretched, heat is released and the temperature of the bead rises. When it contracts, heat is absorbed and the temperature of the bead falls. Now a second chain is added to the tank. It also draws in its ends and the two chains soon entangle. If one end of each chain is pulled, they slide past each other and are separated. When released, it takes some time and substantial agitation before the chains entangle again. Likewise, pulling this uncured rubber makes it flow or deform. It does not recover completely because the molecules slide past one another just as the beads did. Here is a cured or vulcanized sample. It is tough because its molecular chains are chemically bonded together or cross-linked. These beads have been cross-linked to make a single chain. Agitation still causes the cross-linked chains to contract. But pulling on their ends does not cause much flow. Now, the molecule retracts when released just as did the single chain. Some cross-linking thus inhibits permanent deformation without seriously interfering with the coiling caused by agitation. Cross-linked rubber is strong as this tensile test shows. The sample's resistance to stress increases steadily up to the point of rupture. Here is its stress-strain curve. Stress resistance remained quite low, up to about 500% elongation. Then resistance increased substantially. This second curve is for a branched polyethylene. The tensile strength of the rubber just before fracture is actually higher than the plastic. Part of this strength is due to the crosslinks. However, introducing too many crosslinks results in a hard, stiff rubber. All the desirable elastic properties are eliminated. Hard rubber is permanently set during curing and is therefore called a thermosetting material. Clearly, the giant size of rubber molecules and the freedom of each molecule to contract or stretch out have a great deal to do with the unusual properties of rubber. In this film, you have seen how size and shape Structural regularity and polar forces affect some of the properties of polymers. We have discovered a great deal about these materials since Staudinger, Carruthers, and others originated polymer science in the 1920s and 1930s. But there is much yet to be learned.